Yeah, this is ethane. I just have 2 carbons and I have a single bond there. The prefix for 2 carbons is eth, and so we call it ethane. So 1 carbon is methane. If you replace a hydrogen with a CH3 group, you now have ethane. So here's a model, and as soon as you get a hold of a model, it's nice to just like twist things around. Apparently that single bond there, it's easy to twist it around. Maybe you discovered that already. So as you twist it, you start to wonder. I have sort of different orientations or conformations that I could twist this around in. And so a word that's short for conformation is conformer. So I'm just thinking around this carbon-carbon single bond, how twistable it is, and how might I arrange these hydrogens relative to each other? Like what if I line them all up? It's an interesting arrangement. When I line them all up, it's got a nice symmetry. Let's draw that. Let's think about carbon connected to carbon. And then if I line them up, I've got these 2 hydrogens in the same plane. And then I have a wedge here. And then this one's going to be a dash. And then on the other side, I've got my wedge and my dash. So that's with them all lined up. And then I look at that and I think, well, what if I change it a little bit? Instead of having them all lined up like that, what if I turn one of them? I twist a little bit. Now everybody kind of has their own space. Nobody's lined up. Let's see, lined up again. Lined up. And then if I twist them, so we start to think in terms of Vesper theory, the idea that sort of atoms and bonds kind of like their own space. Well, here, if I've twisted them, I've kind of made a little more space for that. So this we might refer to as a staggered conformation, a staggered conformer. Whereas when I line them all up, like originally, it was very beautiful, but it's kind of like the 2 hydrogens here are eclipsing each other. So that's eclipsed. So this diagram is an eclipsed conformation. Here's a staggered one. Staggered. So how should I draw that? Well, I can see that this sort of zigzag here, this hydrogen, carbon, carbon, hydrogen is all in the same plane. And this is going to be a wedge and a dash, wedge and a dash. So let's draw that. So carbon, carbon. I'll keep my hydrogen up like that. It's this one I'll rotate down. So I'm rotating around that single bond. And then I have the wedge dash. And this carbon I'm keeping the same. So this is the staggered conformer, and this is eclipsed. And notice we're not making any new molecule. I have no isomer here. I'm just thinking about the flexibility around this carbon-carbon single bond. I'm just twisting. So I still am talking about ethane, but I'm aligning the hydrogens up in a different way. And, this is a lot to draw. We actually have another drawing tool to represent eclipsed and staggered, and that's something called a Newman projection. Because we're drawing in a 2-dimensional world here on the paper. So I'm taking my 3-dimensional object and I'm going to project it to make something 2-dimensional. So I'll start with this staggered conformation. And the projection is, take a look at it down the carbon-carbon bond. So we want to look at it like this, I'm trying to hold it up right. And notice how it is going to project flat onto the paper. And so I'm going to draw that. So the way we draw this conformation is we like to take a little circle, and then this carbon in the front is what we see best. So I'm going to draw these 3 hydrogens out front. And then behind the carbon I'm not seeing, so I'm not going to write that, but I do see these bonds coming out. So I'll make them come on the outside of the circle. Okay, so that's called a Newman projection, and that is the staggered conformer. Now what about the eclipsed? So if I turn it to line it up, and I draw a Newman projection of that, start with the circle again. My front carbon has these 3 hydrogens. See that? Looks like 120 degrees. That's flat. We know in reality that angle is 109.5 because this is a tetrahedral carbon. But looking flat, it looks like a 120. It's called a dihedral angle. Anyway, here's my hydrogens. Now the carbon in the back we can't see again, and the hydrogens in the back we can't really see. But on our Newman projection, we'll cheat just a little bit on the side, and we'll just draw that second line. So that's eclipsed. Now we could do things like replace a hydrogen with something else. Like maybe that's a chlorine or a fluorine. And we think, okay, this is eclipsed. If that fluorine is kind of lined up with this hydrogen, maybe they don't like it. Maybe they want their own space. And so now it becomes important whether it's really going to be eclipsed or whether this would give a little relief from some of the repulsions felt. Maybe staggered makes more of a difference than eclipsed in terms of arrangement to minimize the overall energy. And then if we even have something on the other carbon, now it starts to really matter. So we think, wait a minute, we don't want to eclipse these groups. That would be a lot of repulsion in there. So we probably want to stagger them. And then we might even want to stagger them so much that dihedrally they'd be like 180 degrees apart between the green and the red. So maybe I'm going to draw something like that. Maybe here's a circle. We always start with the circle. And I got this green one. What do we want to call it? Like fluorine. And I've got the 2 hydrogens. And then in the back, I have some hydrogens sticking out here so that this is a 60-degree dihedral right in there. And then down here, I put that, what's that? Like, we could call that an oxygen. Oxygen's probably going to need something else attached to it, like a hydrogen. So this is like an OH or an alcohol group. So those are fully staggered. I mean, certainly this would be staggered, but maybe that's not quite enough space. Maybe fully staggered is really what we want. Fully staggered. We're going to say that staggered positioning would be the most stable. That's the most stable arrangement. That's the preferred arrangement. If I twist it around, I'm not getting any different molecules, still the same molecule. But because I've spaced it out, the molecule is most likely to be found with this staggered arrangement.